Anybody have any questions about anything before we get started on new stuff?
Dr. Joe,
Yeah.
on the homework, do you want us to show so we can just do the reduce row echelon form button on our calculator?
Yes.
We need to do that, but for determinants, do you want us to show the work for that?
For
For determinants.
I already collected homework on determinants, right?
Yeah, we have to do some determinants on the homework though to show linear independence or.
Oh, to set up an equation? Is there one like that on the homework?
I think it's the second question on the homework. It asks. I don't have it with me.
That's okay. I'm trying to flip back to the. Oh, do you need to do the determinants of the Wronskian, that one?
Yeah, I think so.
I'm not sure how you would do that on your calculator since it has functions in it.
No, what was it?
It was number 11.
It's number 11. On the first like page 230 something.
Oh, maybe I'm looking at the wrong page. Nope. Which page are you on? Sorry.
This is 239.
Number 11.
Yeah.
Determine where it says determine whether the given vector span R3.
Yes.
I mean, you can do it with a determinant. I would have. You're gonna have a hard time doing it with a determinant for the second two because there's 4 vectors there, so it won't be square. I would anticipate with that one for 11, you would just put it in the matrix and row reduce.
Yeah. Okay.
That's what I was expecting. I mean, if you've got well, except for the next test, will have determinants on it. But as far as past the problems that are in chapter 2, if you've got a problem that asks you to do a determinant and it's just numbers in it, you can use your calculator for that. I'm fine with that.
Yeah. Okay. Sounds good.
Yeah. I was confused because I didn't know that. I don't think there's anything in that section 2 that would have required you to take a determinant. That was why I was confused. Sorry.
Yeah.
My apologies.
I think a couple of the book, like in that same chapter, they show how you can do it with determinants.
Oh, I gotcha. Well, yeah, you can't. If it's square, you can absolutely do it with a determinant because when it's square, you're basically checking whether or not the matrix is invertible. And the determinant is a check for that too, so you can do it with determinants as well.
Dr. Joe, where are we turning in our homework on Friday?
There is a Dropbox on Moodle that I set up, and you can just upload your files there.
Okay.
Yep. What I would suggest is there's a couple of apps out there that you can you basically take snapshots with your phone and convert them to PDFs. One of them is called Cam Scanner. It's the one I used. It has a very thick pen. I wanted to change that. It will let you just snap a picture with your phone and instantly convert it over to a PDF. And the PDFs are smaller. But you can also one of the reasons why I like it is because you can turn it into a black and white photo, so it doesn't save as much information, so it's not as big of a file. So you can upload it quickly. But you can use whatever you want. I'll deal with however you get it to me. Any other questions at all?
I have a question about the Wronskian. So whenever we use that, will it be with trig functions?
Not necessarily. It could be with exponential functions as well. Let's see if I can add a page in here to this. Maybe. There we go. There it is. So if we have one that, let's see, this is number 21 on page. Did I ask? Which one did I ask you to do? I don't remember off the top of my head. Was it 21? I don't remember which one it was. It doesn't matter. This is on page 249. One of the problems you have is the set of functions e to the x e to the x, and x squared e to the x. So it doesn't have to be trig functions in this one. So you would still do the same idea, though. So you would set up your first row as just the functions. And then how do you get your second row? What do you do?
Take the derivative.
Yeah, you would take the derivatives, right? So this first column is pretty easy because I would just need to take the derivative of e to the x, so I get e to the x. In the other ones, you would do the product rule. So this one would give me e to the x plus x e to the x. And this one would give me what? 2x e to the x plus x squared e to the x. And then I would do the second derivative. And basically, with these, you're going to take enough derivatives so that you fill in a square matrix so that you can take a determinant. But it doesn't have to be trig functions. It can be any types of functions that you want. As long as they're differentiable, I should say. That's an important part. They can't be functions that you can't differentiate. Does that make sense?
Yes.
Any other questions at all? All right, cool. Okay, so let's go on to new stuff. So I sent out that file yesterday with some notes here that we're going to go through for section 5.4. Just to do a couple of easy examples, and this is just stuff that we've talked about in previous sections. We talked about span. Actually, that was before break, but we talked about span back in section 5.2. And then linear independence, of course, was just what we finished up in section 5.3. So remember, for checking whether or not a set of vectors is linearly independent or if it spans, the whole idea is to put the vectors, if you can, into a matrix and put it in a reduced row echelon form. Well, in this case, when I take that set of vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1, I already have a matrix that's in reduced row echelon form. So, from the stuff that we did in section 5.3, we can tell it's linearly independent because we get a pivot in every column. That tells us that we don't have any free variables at all. So that if we were to set up the homogeneous system, if I think about augmenting 0, 0, 0 here, I know that if I were to solve that associated homogeneous system, I would get C1 equals 0, C2 equals 0, C3 equals 0. So that's how I can tell whether or not it's linearly independent. But the same thing tells me whether or not it spans, because remember, for span, instead of having 0, 0, 0 here, we would have something like A, B, C that we augmented. And then we're interested in, no matter what the A, B, and C are, can we solve the system? Well, again, looking at the reduced row echelon form, well, yeah, because right now it's already in reduced row echelon form. I can see, no matter what I have here for A, B, and C, I can solve the system, right? I can find the constant that gives me A for the first component, that'll give me B for the second component, and that'll give me C for the third component. So when we do linear independence, just to rewrite this down, when we do linear independence, the reduced row echelon form has a pivot in every column. For span, we had the reduced row echelon form has a pivot in every row. So, and just put it in other words, the linear independence would say that if there's a solution, it's unique because I have a pivot in every column. I don't get any free variables. The pivot in every row says no matter what a vector I try to put on the end, I can always solve it. Okay, so the linear independence part is what gives you the uniqueness of a solution. The span part is what gives you the existence of a solution no matter what. So there's a existence and uniqueness part that's going on embedded in this. Okay. We can do the same thing for the second example here. So again, it's not hard to check that this is linearly independent and spans P2 because we're going to have the same kind of scenario, right? Remember, we take the coefficients on the polynomial polynomials and make those into a matrix. So again, we get 1, 0, 0, 0, 1, 0, 0, 0, 1. It's exactly the same scenario that we had in the previous example. So it's not hard to check that this set is also linearly independent and spans all of P2. Because again, it's linearly independent because we have a pivot in every column, and it spans because we have a pivot in every row. All right, so this leads us to our next definition, because both of these sets have both of those conditions that they satisfy. They have it's linearly independent and it spans. So that gives us the idea of what we refer to as a basis. So we're going to start with V being a vector space, and S is going to be a non-empty subset of V. Then we say that S is a basis for V if, well, it has to satisfy both those two conditions. So the first condition is that S is linearly independent. And the second condition is that S spans V. Okay. Just to remind ourselves of what we mean by what this statement means. This means every vector in V, every vector in V can be written as a linear combination of vectors from S. Okay. Any questions so far before we do the next example? Hopefully this example will make it a little bit easier to see what's going on. That was weird. Apparently Siri thought I was talking to her. That was what the beep was in the background. Sorry about that. All right, so let's do the next example. So we want to show that this is a basis. This is not supposed to be a period. This should be a comma here. We want to see that. Well, want to show that the 1 plus x, the 1 plus x squared, and the 1 plus x squared plus x cubed is a basis for P3. Okay, so by the definition of basis, I have to show that this set is linearly independent, and this set spans all of P3. Okay. So notice that we can answer both of those questions by setting up a matrix and row reducing, right? That's how we figure out both of these things, correct? That was what we just talked about at the beginning, that to be linearly independent, the reduced row echelon form has to have a pivot in every column. To span, the reduced row echelon form has to have a pivot in every row. So let's set up our matrix. Our first column, really what's nice about polynomials is that as long as you're consistent with how you put in the coefficients, it doesn't matter how you put them in. I think I mentioned that last time. You'll notice that in your textbook and the way that I write them, usually it goes from, we put the constant and then go up. I know that's not usually how you do that when you do algebra class, right? You're used to writing the highest degree term first and going down. Either way is fine. It does not matter, just as long as you're consistent with how you're putting them in the columns of the matrix. So this one has a constant term of 1 and then zeros for the other coefficients. That's the first one. The second one has a constant term and an x term with coefficients 1 and then zeros, and then so on down the line. So this would be the matrix that we would set up. Notice, just as a kind of a review idea, this is an upper triangular matrix, right? Because we have zeros below the main diagonal. Again, this is just stuff to mention. Remember, to be a basis, it has to be linearly independent and span. So the only hope that we have of a set being a basis is when we construct this matrix that we have, it needs to be square, right? Because if we're going to do the reduced row echelon form, we have to get a pivot in every column and every row for it to be a basis. If it's not a square matrix, we don't have a hope of it being a basis, because either we won't have enough columns to get a pivot in every row, or we won't have enough rows to get a pivot in every column. All right, anyway. To do the reduced row echelon form of this is fairly easy because I don't need to put it in my calculator because it's already in row echelon form, so I would just need to work above the main diagonal, but I already have 1s on the main diagonal. So it's not too hard to see that the reduced row echelon form for this is going to be the identity matrix. So we'll say that, I'm just going to label it as S. We can say that S is a basis for P3. Any questions on that one? Okay. Well, let's go on then to some other stuff here. So one of the questions is, why do we care about these things? And I think I've mentioned this again, something as before break, but why do we even care at all about a basis? Well, the theorem says that if we have a basis for a vector space, then any vector in V can be written as a linear combination of S, of the vectors from S, in exactly one way. So just before we do the proof of this theorem, let's go back up to the first example where we had this set in R3. If you've had Calc 3 or probably some physics classes as well, you'll recognize these vectors as being referred to as ij, and k. Doesn't matter what I call them, but I notice that any vector in R3, if I write it as a, b, c, that's going to be a times I plus b times j plus c times k. And that's the only way I can write a, b, c in terms of I, j, and k. There's no other numbers that I can use to get to write a, b, c in terms of the I, j, and k. And so that gives us the idea of being coordinates of that point, or coordinates of the endpoint of the vector in R3. So we have the idea of coordinates pops up. So that's why we care about the fact that we have bases. We have this uniqueness idea of the representation so that we get coordinates of a particular vector with respect to a basis. So let's see if we can do this proof and then do a couple of examples along those lines. All right, so we're supposing that S is a basis for V. S is a basis for V means that S is both linearly independent and it spans. Well, first let's do span. So W is an element of V. So since S spans V, that means I can write W as a linear combination of the V's in S. So we could say that there exists a C1, C2, out to Cn that are scalars such that C1v1 plus C2v2 plus CnVn is equal to W. Okay. Now notice, I want to emphasize this because this is again going back to proof techniques, and that again linear algebra is a nice introduction to proof type of course. Notice that the theorem says that we're supposed to be able to write W in exactly one way. So when you're proving things in mathematics that say exactly a certain number, the typical way to prove it is to show that there's at least one, or at least that many, and then at most that many. In this case, we said, just writing down the fact that it's a basis, we know that it spans, so there exist those constants that give us that W. We know that that's the existence portion. We've shown that there is at least one way to write W as a linear combination of the V's. Okay, does that make sense what I'm saying there as far as the existence part goes? We okay with that?
Yes.
Yeah? Okay. So then the other way to show uniqueness in mathematics, this is typically the way you prove uniqueness in math, is that you assume that you have two, and then show that they really had to be the same thing. You do this kind of a proof, if you remember back to discrete math, you do this kind of proof when you show that functions are one-to-one. You assume that two outputs are the same, and then show that the inputs are the same. It's the same kind of concept, right? We're going to assume that we have we're going to assume we have two representations here of W, and show that they really had to be the same. So for uniqueness, let's assume that, or we'll suppose, that we also have D1, D2, out to Dn that are scalars, such that same thing happens. D1 V1 plus D2 V2 plus Dn Vn equals W. So I'm assuming here that we have a second way to write W as a linear combination of the V's. Now notice for the existence portion, we use the spanning aspect of S to be able to get our first linear combination. To get the uniqueness aspect, which property of the basis do you think we're going to use? We already used the spanning property, so which property do you think we're going to use now?
Linear independence.
Yeah, the linear independence part, right? So to be able to use the linear independence, what vector am I going to have to see a linear combination that's equal to? What's the definition of linear independence say? We have a linear combination that gives us what? Which specific vector? With our definition of linear independence, what linear combination specific vector are we writing as a linear combination to start with? Remember our definition? We said if we have a linear combination that equals a specific vector, what's the specific vector on that right-hand side? The zero vector, right? Cool. Okay, so let's look at these two equations. How can you combine these two equations to get the zero vector involved, do you think?
Subtract them.
We can subtract them, right? Notice I've got W on the right-hand side of both equations, so I should be able to subtract them and get the zero vector involved. So now we have, if I just subtract and combine, we'll have C1 minus D1 times V1 plus C2 minus D2 times V2 out to Cn minus Dn Vn is equal to the zero vector. I just subtracted and combined terms using our properties for our vector spaces to be able to do that. And then again, the whole reason why we knew to subtract is because we knew we needed to get the zero vector involved, because we need to use the fact that S is linearly independent, and the definition of linear independence involves a linear combination, which we have on the left-hand side here, that's equal to the zero vector. So since S is linearly independent, what does that tell us about the individual scalars then? What do they have to be? If we have a linear independent set and a linear combination that gives us the zero vector, what do the individual scalars have to be?
They all have to be zero.
They all have to be zero. Good. So we have C1 minus D1 has to be 0. C2 minus D2 has to be 0. All the way up to Cn minus Dn has to be 0. So what does that tell us about all of the C's in relation to all of the D's? They're equal. Good. So C1 has to equal D1, C2 has to equal D2, and so on down the line. Cn has to equal Dn. So did we really have two different representations here, up here? Or did we have the same representation just written with different letters? It's the same representation, right? So that's what we just proved here, is that we assumed we had two, and really they had to be the same. We didn't have different constants here. Questions about that proof?
Do we need a conclusion for it?
Say that again?
Do we need a conclusion for it? Like a formal conclusion? Like
Oh, so you could just rewrite what the formal conclusion is. This pretty much gets it taken care of, right? If you want to write a conclusion statement, you can. So you could say thus every vector in V can be written, I'll even just say uniquely, as a linear combination of the vectors in S. You can write it that way if you'd like.
Okay, thank you.
Yep, you're welcome. All right. So let's see about an example here. So let's look at this particular example. It says, first show that this set is a basis for R3. So that's part A. So what do we need to do to show that this is a basis?
Show that it's linearly independent and it spans.
Good. We need to show that it's linearly independent and it spans. So how do we show that all in one step, essentially? What do we need to do?
Put it into a matrix and reduce for echelon form.
Cool. Good. So put it in a matrix. Make them the columns of the matrix. And convert it over to reduced row echelon form. And I should have opened up my calculator first. Let me see if I can get a calculator open. I forgot to open the calculator before I started, so bear with me for a second. Oh, that's what I should be doing. That would make more sense. All right. Can everybody see my matrix? All right. So go to second matrix and over here and edit. And we had a 3x3. And I've already forgotten what the elements of the matrix were. Can you tell me what they are?
5, 4, -3, 2, -1, 1, -7, 3, 8.
All right. So we'll go over to matrix and then reduced row echelon form of A. And we see the identity matrix, which again means we have a pivot in every column and we have a pivot in every row. So we see here that we really do have a basis for R3. Is that part okay with everybody? Okay. And why won't you let me go back to what I was doing? Here we go. All right. So going back over here again, the reduced row echelon form gives me 1, 0, 0, 0, 1, 0, 0, 0, 1. So the second part asks you to find the coordinates of this vector relative to S. So what that means is, when we say the coordinates, just as the definition here, when we say the coordinates relative to a basis are, well, this is how we write it. We have a vector v and we write a little subscript s. This is going to be equal to the c1, c2 out to the cn, where the c's, oops, let me write this as w, sorry. where the c's are the scalars in your linear combination that give you w. Again, this is the whole reason why we even care about the uniqueness part. Sorry, the existence and the uniqueness part. This is why we care about vectors in general. Sorry, bases in general. Is the fact that I know that I can do this and there's only one way to do it. So this definition of being coordinates is well defined. I don't have a different set of coordinates that point to the same vector. You've dealt with non-unique representation of coordinates before when you've taken Calc 2 and dealt with doing things with polar coordinates. Or in Calc 3 where you've done things with cylindrical or spherical coordinates. You know that the coordinate representation in those particular coordinate systems is not unique. Okay? You have multiple sets of representations for the same points, which is why a lot of times you want to restrict yourselves. It's like in polar, you might say, okay, use an angle that's only between 0 and 2 pi. Okay? So you don't get repeated things. So that's why we care about the idea of basis here, is because we want to make sure that we have not only existence but also uniqueness, so that this idea of being coordinates is well defined. And basically all we're doing here is the same stuff that we did earlier in the semester. We're just going to set up a system of linear equations. All we need to do to find the coordinates now, we're looking for these particular constants, so we're going to set up a system of linear equations and solve it. So going back to the original, all I want to do is take that same matrix that we started with our basis and augment the vector that we're interested in. Think about why this is the case, how we could come up with this particular system. Notice when you take C1 times V1, it would be C1 times the first component. When you take C2 times V2, you get a C2 times the second component. When you take C3 times V3, you would get C3 times the third component. And you want it to equal that first component in this vector. So that's how we're getting that first equation, and so on down the line. So again, then we would take the reduced row echelon form and row reduce. So those numbers are 24, 13, and 67. Oh, it doesn't like to switch on me. So let's see if I can go back over here. So let's go back into edit this matrix. I need to augment it with an extra column. And the first number was 24, is that right? And the next one was 13?
Yeah.
And then negative 67?
Yes.
Okay. Thank you. I appreciate it. All right, and then we do the exact same thing. So all I did was go into there and augment the vector that I'm interested in. And go back and just re-row reduce the same matrix. So I just used the second entry command to do that, so I didn't have to go back in and find it in the menus again. So there is our reduced row echelon form. We get 6, negative 3, negative 2. So if I go back over here, this reduced to 1, 0, 0, 0, 1, 0, 0, 0, 1. What did I say? 6, negative 3, negative 2? Okay. So we would write, the notation we would use is that the coordinates of 24, 13, negative 67 relative to our basis S, so we use that little subscript S here, would be 6, negative 3, negative 2. Okay, so again, emphasizing what this actually means here, going back up to our basis. This was our basis, right? So what this means, this 6, negative 3, negative 2 means that if you take 6 times 5, 2, negative 7, minus 3 times 4, negative 1, 3, minus 2 times negative 3, 1, 8, you get the vector 24, 13, negative 67. Questions on that? I hear none. Okay. All right. So now this was a weird basis for R3, but in general we have some what we refer to as standard bases for various spaces. Going back up to the very, very first example we did, remember we had the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1 for R3 and said that that was both linearly independent and spanned. Notice that when we took that set of vectors and put them into the matrix, into a matrix form, we automatically had the identity matrix. We didn't have to do anything to it, right? It was already in reduced row echelon form. We saw the identity matrix. So that's why we refer to that as the standard basis. So the standard basis for R3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. And we can generalize this, right? When we think about Rn, we think about what would have to happen to have the standard basis. Again, think about it as when I plug those vectors into the matrix, into a matrix form, I automatically get the identity matrix. Well, that means that that first vector should be a 1 in the first component. The second one should have a 1 in the second component, and so on down the line, until the last one only has a 1 in the last component. Now, again, from Calc 3 ideas, a lot of times you refer to these as I, J, and K. Now, if you try to do this in general for things in Rn, you're going to run out of letters. So one of the things they use for these standard basis vectors, and this is pretty standard in any textbook that you look at, for standard basis vectors, they use an E1, an E2, out to an En. The reason why we use the letter E is because when we talk about identity, these look like the well, when you put them in a matrix, you're going to get the identity matrix, and the German word for identity is Einheit, which starts with the letter E. That's why the E's are used. You probably didn't care, but I thought I would share that information anyway. That's why we use the letter E.
Thank you.
Mm-hmm. All right. So what do you think the standard basis is going to be for P2? Thinking about what we did at the beginning of class here, what do you think the standard basis for P2 would be?
Polynomial with just the coefficients of 1.
Okay, so yeah, the 1 and the x squared, right? Okay. So think about why this has to be true. Think about how you would write a general second degree polynomial. You need a constant, you need an x term, and you need an x squared term, right? That's how you write a general second degree polynomial. And if I think about writing it in linear combination form, if you will, this would be a times 1 plus b times x plus c times x squared. Just being pedantic, but this is, I have a constant times the first vector, a constant times the second vector, a constant times the third vector, and it gives me those coordinates that you're familiar with, the coefficients. Okay. So when we go in general for Pn, how do you think we're going to write the general standard basis for Pn?
Just the same thing, going basis to 1, x all the way up to epsilon.
Good. All right, because think about how you would make an nth degree polynomial. I need a constant term, I need an x term, I need an x squared term, an x cubed term, all the way up to an x to the nth term. So that would be the standard basis for Pn. All right. So let's think about matrix spaces. So this M23 is the set of 2 by 3 matrices. Now let's think about how many we would need before we start trying to fill in what we think might be the standard bases. Okay, because this idea is leading us to the next concept of dimension. So notice that up here, when you have an arbitrary arbitrary vector in R3, I have 3 places that I have to fill, right? I have to fill a first coordinate, a second coordinate, and a third coordinate. So I'm going to need 3 vectors in my basis to be able to fill in those 3 coordinates. Or if you extend it to Rn, I need n elements in my basis to fill in each of the n coordinates. For polynomials, notice here I needed 3 polynomials to help me fill in the 3 components that I need. In general, if I have an nth degree polynomial, I need n plus 1 things filled in because I have coefficients for x to the first all the way up to x to the n, plus an extra one for the constant term. All right, so let's think about 2 by 3 matrices. If I fill in an arbitrary 2 by 3 matrix, how many spots do I have to fill in?
6.
6. So how many elements do you think might be in a standard basis?
6.
6, right? Or okay, so I better have six entries. And then think about the different components that we have to fill in. I got to fill in upper left-hand corner. And then I'll probably not worry about filling in anything for that one. And then I've got to fill in middle first row. I've got to fill in upper right corner. Lower left corner. Middle second row. And then lower right corner. One thing that you've probably noticed, or may have noticed, or maybe you haven't even thought about at all because you don't really care, but one thing that I might have noticed is that since we're doing the vector space for matrices under ordinary addition, and the vector space for the real the RNs as ordinary addition, sorry. We're essentially doing the same operations. Notice I can think of these as vectors in R6, right? If I just wrote them out all the way across rather than one row and then the next. So notice that this looks a lot like what we would have had for a standard basis for R6. Then in general, for m by n, you would use, the standard basis would be, let me just use it as, I say I have it a sub ij. So let's say we have, that's our matrix. Maybe I should not use i's and j's. Let's use, let me use a k and an l. Let's not write it that way. Basically, I want to write this as I have a 1 when I is equal to k and j is equal to l, and it's 0 otherwise. I'm just trying to think of a good way to write what the entries have to look like, right? You're basically going to put a 1 in each of the entries where you need it for mn. Any question on standard basis stuff at all? All right. Okay, cool. All right, so let's talk about why I've emphasized this idea. So I already mentioned that to fill in the different spots for, say, Rn or Pn or M sub Mn, we have to have a certain number of spots that we have to do. So that's going to lead us to the idea of dimension. Before we get that, though, we need a couple of definitions. So the first definition is we say that V is finite dimensional if there exists a basis for V that has a finite number of vectors in it. So each of the vector spaces that we've talked about today have all been finite dimensional because they all have had a finite number of elements in a basis. So the definition for infinite dimensional, you can probably guess if there does not exist. A basis for V. I don't know why I keep saying B. Has a finite number of elements. Okay. So probably the prototypical example of infinite dimensional vector space that we've talked about so far would be your function spaces. So like continuous functions on A, B, or continuously differentiable functions of nth order differentiable functions on A, B. This is probably the best example of an infinite dimensional vector space that we have right now. There are others, but they're weirder than what you were going to deal with. Just think of just the function spaces as being the ones that are going to be infinite dimensional. Most of the things that we're going to talk about are finite dimensional things. All right. So, pardon me. What the next theorem leads us to, and I'm not going to try to prove this right now because just because we only have about 4 minutes to talk. So what this leads us to is that let's think about what this is saying as far as a conclusion goes, and then we'll come back and prove this next time. So what this says is that if we have a basis for V, and I have another subset in here that has more elements in it than what this basis had, then the set had to be linearly dependent. Okay? Let's think about why, in terms of just Rn, let's think about why that would be true. What if all of these vectors were in Rn? Well, then if I try to put it in a matrix form, now I'm not saying that all of these had to be vectors in Rn, by the way, but I'm just saying assume they were to start with. Say I was trying to check whether or not this was linearly independent. How many, if these are vectors in Rn, how many rows would there be? If these are all vectors in Rn, how many rows would we have going down here? Hopefully it's clear we have m columns, right? How many rows would we have? N rows, good. Okay. So we have more columns. If we're assuming that m is greater than n, we have more columns than we have rows, right? Okay? We have more columns than rows. So can we possibly get a pivot in every column? If we have more columns than we have rows, can we get a pivot in every single column? No. So that tells us that the set is not linearly independent, or it's linearly dependent. Does that make sense? Okay. So this is the exact same idea that we're going to do when we actually do the proof. We're going to set up, the proof of this is exactly this kind of explanation. We'll set up a system of linear equations where we have more unknowns than we have equations. And we'll set up a homogeneous system. And when we do that, then we know that we have non-trivial solutions, which means it cannot be linearly independent. So we'll talk about that next time. You've got your homework that's due on Friday. Like I said, I set up a Moodle Dropbox for your homework. Just upload your files there. Again, if you can convert them to PDFs, that would be great because, again, they're smaller. But if you can't, that's fine. I can deal with whatever pics. Just put them in that Dropbox. It'll be a little bit easier for me to collect them that way because I'm collecting everybody's homework from all 3 of my classes electronically. So if I can get them, instead of having them all coming into my email, if you can put them in Dropboxes, it'll help me organize things. So I'd appreciate it that way. Any questions before we end this?
I had a question about
Yeah.
Monday's lecture, I guess.
Okay.
Did you post the whole video on the YouTube, or?
I thought I did. Is it not there?
Well, the only one that I saw was like a 17-minute one, and it just had like the examples that you went over, that we were going to go over in class, but obviously we didn't get back to class.
Oh. Well, I will go back and check on that because I thought I had posted that. So thank you for telling me that. I did not know it wasn't up there. I will take care of it.
Okay, thank you.
Yep, you're welcome. I'm going to write that note down right now so I don't forget. Anything else? All right. Well, we will talk to you on Friday then. Everybody have a good one. We'll see you then.
Bye.
Bye-bye.